Okay, today we'd like to derive the expression for fermion propagator. Until now, we have constructed the free field Lagrangian for spin 1/2 particle. That was, if I make use of left-right derivative, then I over 2 1/2 I psi bar gamma mu derivative psi minus m psi bar psi. If I expand this, if I take the derivative to the right side, I have positive sign. If I take the derivative to the left side, I have negative sign. And here, it used to be derivative of psi bar, and what I have done is just extended this bar to the derivative. If I don't, you will find the current vanishes. So let us substitute gauge covariant derivative to the covariant derivative. Then everything except for the term that is proportional to the gauge field is just the free field Lagrangian for that particle. And then I have 1/2 I psi bar gamma mu, and ground mu is replaced with IQA mu, right? And psi. Here I have IQA mu, but take the complex conjugate, so I have minus IQA mu star. And psi bar, there is no derivative at all. Psi bar gamma mu psi. We recall that if the particle has a electric charge, then the wave function and its complex conjugate are different in general. However, if particle does not have any charge, then wave function must be real. Okay? So even though I take the complex conjugate, because light, photon, does not have any electric charge, A mu star is the same as A mu. And I have proved this, I have replaced with A mu. Then two contributions is just a minus 2q psi bar A slash, there's a Feynman slash is defined by A mu gamma mu. This is a simple abbreviation for this product, sum over mu. Okay? The factor of 2 cancel this 1/2 over a vector. So Lagrangian for the electromagnetic interaction, including photons of free field, so we have constructed the QED Lagrangian for electron and photon and their interaction. And this is gauge invariant, right? This is gauge invariant, F mu nu is F gauge invariant. It is not easy to see whether it is gauge invariant or not, but we have shown that in the previous case for the charge scalar field, d mu changes, transforms like if I make a gauge transformation psi to u psi, then round mu psi also transforms like u round mu psi. Okay? So it is invariant on the gauge transformation, and it is also Lorentz invariant. Requirement of the Lagrangian density is that action must be Lorentz invariant, and action the integral measure is Lorentz invariant, so Lagrangian density function must be Lorentz invariant. So we have not explicitly showed that this one is a Lorentz invariant, but actually it must be Lorentz invariant. We have to construct a theory that should be Lorentz invariant. And previously we have shown that derivative is a 4-vector and it is Lorentz invariant. So this guy, psi bar gamma mu psi, should be a 4-vector to make the whole object a Lorentz invariant. So it is a Lorentz scalar, and the previous class I told you psi bar psi is Lorentz invariant, the Lorentz scalar. It is evident each term in pre-particle Lagrangian must be Lorentz invariant. Right? So it is a Lorentz scalar. Alright, why don't we find the equation of motion for this interaction? Then let us vary the psi bar field. Then the result is like that. If I take the derivative, this guy disappears, and over derivative means gamma mu, so minus I, round mu, gamma mu, round mu, psi. If I take the derivative with respect to psi bar, then this one disappears, and this is 0. So minus m over vector negative changes this plus m psi and plus q a slash psi. So if I expand this, equation of motion is like that. But we know the Dirac equation has this one equals 0 with over vector negative sign. So let me move this guy to the right hand side and exchange left and right. The final expression for the equation of motion is like that. So it has a little bit awkward form, but let me just call it as a current. And to solve the general equation for the general solution for that, we know that it is good to know the Feynman propagator that is equal to delta function. Okay? You know, this guy has a matrix, 4x4 matrix, left hand side. So this guy is multiplied by Feynman propagator that has a 4x4 structure. And after the multiplication, it should be proportional to identity matrix in 4x4 space, and delta function with respect to the space-time variables. Now, let us make use of this kind of trick. Suppose if SF is factorized into two pieces, let's see what happens. This guy is the same as this operator, except that the sign is in front of mass is flipped. If I multiply these two, substitute this and multiply these two matrices, then I get this one minus II minus round mu. They are summed. So I must use different indices. So gamma mu, gamma nu. So nu. I have replaced this one with nu. And round mu. And they can be reordered. Round mu is equal to round mu. So let me add two things and combine them. Then it's just 1/2 mu nu mu, and with the same derivative. The mass squared is still there. Anti-commutation relation for gamma matrix is just what? 2 times g mu nu. So 2 cancels, so it is contracted, so that round squared plus m squared with the over negative sign. A similar calculation can be made. A slash is what? A mu round mu, A mu gamma mu If I square this, I have a nu, ground mu, gamma mu. And again, I can, because a mu and a nu, they are just a number, and they are identical one. Let me just double this and multiply 1/2. Then again, I get final result is a squared, 4 vector squared. Okay, so if I make use of this relation, then this partial differential equation is reduced into the form round squared plus m squared f of x equals minus identity. Minus sign comes from this minus identity delta function. This is the equation for Feynman propagator of scalar particle. So we don't have to solve it again. We previously have derived it already. So the result is just 4-dimensional momentum integral exponential minus I p dot x divided by p squared minus m squared plus I epsilon. Okay, so final result for the S of f, the Feynman propagator, is this over factor multiplied by the massive particle, massive scalar Feynman propagator. Okay, this is this, and I have x derivative. So if I pull this one inside, what happens is I take the derivative of this exponential function. If I take the derivative, this one operate e to the minus ipx, then round mu collects minus I p mu, minus I minus plus I to cancel, so that round mu p mu exponential minus I p dot x. So it is simply written as a p slash. So this is a p slash plus m exponential minus I p dot x. You know, p slash plus m times p slash minus m is a p slash squared minus m squared. Well, if I make use of this relation, then it is just a p squared minus m squared. Okay? So I just think this one is just p squared minus m squared plus I epsilon over p slash minus m is something like p slash plus m, p slash minus m plus I epsilon, and we have p slash plus m, and cancel this p slash minus m plus I epsilon. This is a kind of abbreviation. Mathematically not rigorous, but simple expression that gives actual meaning is that, but simply we usually write like that. You know, propagator, and actually I have to multiply I to the propagator into Feynman rule, right? So real propagator is, in momentum space propagator is just I over p slash minus m plus I epsilon. That is the Fermion propagator. And the equation of motion for this was psi. Okay? Remember, this is psi, not psi bar. So this momentum should be written in such a way that particle, whether it has a positive energy or negative energy, particle's direction of motion. So if it is electron, if it is positron, electron is treated to be coming backward. So positron's case, even in positron's case, we have to flip the direction so that it is expressed in terms of negative energy electron. So the direction, momentum P must be chosen in such a way that electron, a particle, is moving, regardless of the fact whether it has a positive energy or negative energy. You have to choose the direction along the particle's motion. Okay, that's it.